I'm Maria Vukšić. As a mechanical connection between locomotive and wagons in the train, and they transmit traction forces. In world, there is a use of automatic coupler, but in Europe, as you see, all the green area are with the automatic coupler. In America, South and North America, there is a Jenny type of automatic coupler, and in Asia, there is a SA3 automatic coupler that is used. In Europe, these are the yellow area on the map. We use screw coupling system. And in Africa, there is a mixture of other automatic and screw coupling and other system like hook coupling system. These systems are in presentation these systems used in Europe are on freight wagons mainly. The passenger wagons usually have some sort of automatic coupling systems. So in Europe, there is use of rail freight wagons that circulate in all of the Europe. So you can find wagons from Germany, on France, running in on the Serbian railways, and also Serbian wagons that run on other European countries. So when we discuss the failure of the coupling system parts, we can do it by looking at failures that occurred on Serbian railways. These are the elements of the coupling systems. There is a screw coupler as with his element, and draw gear that's basically beneath the frame of the freight wagons. Impact of coupling failure on a safety is what makes these investigations interesting, because when coupling system failed, trains break apart. Actually, there is a division of a train in traffic, and usually it's a source of train breaks apart is a failure of some of the elements of coupling system, or tearing of the brake pipe or hose. Root cause analysis of this fracture of coupling elements are usually fatigue in material, defect or inclusion in material, as well as corrosion and shock load during operation. We can see in a picture example of train breaks apart and failure of a coupling system that's that is shown. Okay. That is show lie down on the tracks, okay, because it's of course failed and fractured. Next, we will discuss some case studies of a coupling system failure, and one of them is in the UK in Camden Road Tunnel, which was occurred in 2007. And interesting about this case is because screw coupling broke between the second and third wagon in on the back of the train when the train starts after standing on the signal, and with the problem of on the brakes from these detached wagons, that was a runaway of detached wagons, and that's a big safety issue on railway traffic. Similar was the case, previous incident, also in the UK some year ago, where the runaway occurred following failure coupling, and runaway wagons ran for almost 5 kilometers in the backward direction and run through the engineered work site. And that can be potentially big risk, because if the train was coming from the other direction, they can collide. Therefore, it's important to know the causes of such a failure. And this analysis done by the accident report members show that broken eye of a shackle, as you can see, have a brittle fracture, followed by the ductile fracture on other side of the eye of the shackle, and with no evidence of fatigue material. Also, it was established that the material hardness was more than a double specified in the prescribed standards. In a conclusion of this report, it was established that the shackle has been subjected to localized heating and cooling. Next case of analysis was for the fracture of screw coupling elements that was occur in Slovakia. And as you can see, fracture occurred when the heavy train accelerated after stop at the signal, and fracture part show brittle fracture, and it was caused by superposition of several factors. One of them is that the impact toughness of the draw hook that was fractured was insufficient, especially at a low temperature that was present at the accident that occurred. It was below 0, and you know that impact toughness decrease their values with the decrease of the temperatures. Also, non-coaxial loading that was caused by the different height of the draw hook axis in between the wagons caused the additional stress, and that with the addition of low impact toughness lead to the brittle fracture of the draw hook. Here is some examples from Serbia. 2 models of failure of coupling elements, coupling links are discussed. One is a sample that failed to ductile fracture, and in a picture with the B was a failure of the element through brittle fracture. And metallography indicate that the B sample was hardened and tempered with the typical temperature for martensite microstructure, and A was normalized with ferrite microstructure. The mechanical properties of both specimens fully meet requirements of European norm that prescribed for these screw coupling elements, and the result of finite element method analysis corresponds with the result with ductile and brittle fracture, and this indicated that the failure of links occurred due to operational load that was higher than allowed, than predicted. Next case of analysis of coupling failure was in Slovakia with the draw hook that have signs of fatigue, and draw hook with analysis showed that the material of the draw hook had all the properties prescribed in standard, but transition radius show here was smaller than prescribed in the standards, so that led to additional load and additional stress that lead to the fracture. Also, additional bending load that was the result from a specific operational condition increased the stress and lead to the fracture of this jaw. One of the cases that was analyzed in fracture that was analyzed in Romania and show fracture surface of coupling links that's also fractured with signs of material fatigue line, and analysis was done also with the finite element method, and material is different from those prescribed in standards. So analysis was done by modeling the longitudinal dynamic forces of coupling system, and based on that, the estimation of total number of cycles of propagation of crack showed that propagation was done in about 1 month period of operation, wagon in operation. Next few slides show some of the fractures of coupling elements that was occur on Serbian railways, but not always on Serbian wagons. As you can see, first one is the fracture of drawbar. Wagon is actually from Bosnia and Herzegovina, and like this fracture of draw hook, similar to the previous analyzed case, was from the wagon from France. In a conclusion, we can classify fracture by the main cause to fracture of fatigue, as a cause is a fatigue of material as a result of dynamic loading and at places of stress concentration. Brittle fractures as a result of corrosion and dynamic loading. Brittle fracture as a result of initial cracks of surface damage at the point of fracture initiation, and most rarely the ductile fracture as a result of overload. Analysis of cases of failure of coupling systems elements shown in the graphic over there are done for the fractures on the Serbian railways in from 2018 to 2020, and they show that the screw coupling elements failure in 21% of the cases of train breaks apart, and draw gear elements failure in 54% of the cases of train breaks apart. That's very concerning, because screw coupling elements are made so that the maximal breakage load is 20 kilonewton lower than draw gear maximal stress. And next and future work was to establish why are the elements of draw gear so oftenly failed at operation in freight train traffic. That was end of the presentation.